Welcome to my channel Simple Concepts by DJ. Today we are going to discuss a topic called as nodal analysis with current sources. This is an important problem. This is an important derivation that is used in circuit analysis for electrical engineering and electronics. Okay, so let's get started with the video lecture. So this is nodal analysis with current sources. So this is the name of the lecture, nodal analysis with current sources. This comes under circuit analysis and network theory, whatever it is. Okay. So I'm going to draw a network, a resistive network. This is a resistor. Now you have another resistor over here. You have another resistor. This is connected to the datum or the reference point. This is connected to the datum or the reference point. You have another branch in which a current source is being connected. Now this point and the current source is being connected. This point is connected to the ground potential. So now here also you have another branch in which another current source is connected, and this is connected, in turn is connected to the ground potential, that is the earth. Okay, so this is the circuit diagram. So now what I'm going to do is, see, let us assume that this current source is producing a current I. Okay, this produces a current I flows. So before that, we want to name the nodes. We want to name the nodes. So let this be node 1. This be node 1, and the voltage that has been developed in node 1 be V1. Similarly, this be node 2, and the voltage that has been developed in node 2 be V2. Okay. So how about these resistors? Let this resistor be R1. The resistor is R1. Let this resistor be R2. Let this resistor be R2, and this resistor be R3. Okay, R1, R2 and R3 are the three resistors. In this circuit you have two current sources and you have two nodes, V1 and V2, and one point is the reference node that is being connected to the earth, that is grounded. So now this current source will produce a current, and that current will go and it reaches the point here, this V1 point, and here the current will bifurcate into two different branches. So let one branch be, for better understanding, I'll keep this point as R2. This point as resistance value is R2 and this resistor value is R3. Okay, for better understanding. In order to avoid confusion, I am keeping this as R2 and R3. So now when this current reaches this point 1, okay, this node 1, the current bifurcates into two different values. So one is I1. A current I1 will flow through the resistor R1. Similarly, a current I2 will flow through the resistor R2. So this current I2 will reach this point, and again further the current will bifurcate. So the current will come here, the current which is passing through the resistor R3 be I3. Let it be I3. And the current which is flowing through the current source, okay, current source, that let that current be I0. Okay, So these are the value of currents and the value of resistor and the nodal points. These are the current sources which is producing two different type of currents. One is I, and another current source is producing a current I naught. Okay. So now what we are going to do is, as said earlier, let us consider this node 1. I am going to consider node 1, and in this node 1 I am going to apply the current law. So if I apply the KCL over here, the incoming current will be considered to be positive and the outgoing current is considered to be negative. So I will be getting I. See, I is a current which is incoming current. So I minus I1 minus I2 minus I1 minus I2 is equal to 0. So now again, I can be written as I1 plus I2, right? I can be written as I1 plus I2. I am naming this as equation number 1. So I need to find the value of I1. So I1 is nothing but I1 equal to, I1 is a current which is flowing through this branch. So I1 will be the ratio between the node voltage V1 and the resistor that is being connected in the branch in which the current I1 is flowing. I1 is nothing but V1 by R1, is V1 divided by R1. Similarly, I2 is equal to, I2 is a current which is flowing through this branch. So when I2 current flows, there are two different node has been developed here. So the difference between the node voltage divided by the resistor value gives the value of the current that is flowing through resistor R2. So I2 will be equal to V1 minus V2 divided by R2. So I have two different types of values, I1, I2. Okay, now I'm going to substitute it in equation number 1. So I equal to I1 is V1 by R1 plus I2 is V1 minus V2 divided by R2. So this will be V1 by R1 plus V1 by R2 minus V2 by R2. So this is the equation I had formed. So now I am taking V1 outside, V1 into 1 divided by R1 plus 1 divided by R2 minus of V2 divided by R2. Okay, so this is the value of current I'm going to name it as equation number 2. So I have got the value of I is equal to this minus this. So I can write, what does this I equation denotes is, I1 is equal to the product of the voltage that has been developed at point 1. Product of the voltage that has been developed at point 1 at node 1, which is V1, and the sum of the reciprocal of the resistors that has been connected to this node 1 minus V2. V2 is nothing but the adjoining potential. When I consider this potential, this node V2, the voltage that has been developed here is considered to be an adjoining potential minus the ratio between the adjoining potential, that is V2, and the interconnecting resistance. This R2 is considered to be called as the interconnecting resistance because it is connecting this voltage V1 and V2. So this is called as interconnecting resistance. So minus of the ratio between the adjoining potential and the interconnecting resistance. So this is how you need to write in your examination by looking at this equation. So this is the value of the current. Now similarly, I'm going to consider node 2. If I consider node 2, it will be similar. I'm going to apply the current law, Kirchhoff's current law. The sum of incoming current will be considered as positive, and the the sum of outgoing currents will be considered to be negative. So node 2 means the incoming current I2 minus I3 minus I3 minus I naught equal to 0. So what I can do is I2 equal to, I'm taking this I3 and I naught to the right hand side of the expression. So the negative value will be converted into positive. So I2 is equal to I3 plus I naught. So I naught, leave it as it is. So I naught can be written as I2 minus I3. I naught can, because I naught is the current, it is the current that is being produced by this current source. So just you leave it, I naught you leave it, but I naught you keep it as it is, and you take this I3 to the other side. So it will become I2 minus I3. I naught equal to I2 minus I3. So the value of I2, you have already found the value of I2. I2 is nothing but the difference in potential between the two different nodes divided by the interconnecting resistance. So I2 we have found. Okay. So what is I3? I3 is nothing but I3 equal to the voltage, the corresponding voltage that has been produced in node 2, that is V2. V2 divided by R3. So V2 divided by R3 is nothing but I3. So you need to substitute this value, these values in this equation. So I'm terming this equation as equation number 3. So I naught equal to I2 minus I3. What is I2? I2 is V1 minus V2 divided by R2. V1 minus V2 divided by R2, okay, into minus I3. Minus I3 is minus V2 divided by R3. So it will become V1 by R2, V1 by R2 minus V2 by R2 minus V2 by R3. So this will become V1 divided by R2 minus V2 into 1 divided by R2, 1 divided by R2 plus 1 divided by R3. I am taking this minus V2 outside the bracket. So it will become minus V2 into 1 by R2 plus 1 by R3. So this is I naught. Now what I'm going to do is, here I'm going to make a small amendment here. See this I naught. See, I'm writing this equation over here. I naught equal to V1 by R2, V1 divided by R2, V1 by R2 minus V2 into 1 by R2 plus 1 by R3, 1 by R2 plus 1 by R3. So I'm writing this equation here once again. So now what I can do is, without changing the value, I'm going to make a small alteration. So this will become, I'm taking a negative sign outside, minus, and with the bracket I'm adding a negative sign for this ratio V1 by R2. Similarly, I'm adding a positive sign here, and I'm writing this expression as it is, V2 into 1 divided by R2 plus 1 by R3. Okay, so I'm taking a negative sign outside the bracket and I am inserting a negative sign to this ratio V1 by R2, and I'm adding a positive sign to this V2. So minus into minus will be plus V1 by R2. V1 by R2 is here. Similarly, minus into plus equal to minus into plus equal to minus V2. So that minus V2 is here. Minus V2 divided by 1 by R2 plus 1 by R3. So by doing this small amendment, the previous value will not get changed. It will be as it is. Okay, without changing the previous value, I am making a small amendment. So this is allowed. Okay, so this will be, see here in this equation, both the equations look identical. Equations, let us assume that this is equation number 4. I am assuming this as equation number 4. See, this equation 4 and equation 2 both look very identical. See, here you have V2 by R2, here you have V1 by R2, here you have V1 into the sum of the resistance in reciprocal form. Similarly, you have V2 here and sum of the resistances in reciprocal form. So what does it mean? I naught is equal to, here I naught is equal to, see I naught, I am going to write here I naught equal to, I naught can also be written as minus of, I am taking this term V2 into 1 by R2 plus 1 by R3, V2 into 1 by R2 plus 1 by R3 minus of V1 divided by R2. So this term I'm bringing it to this side and this term I'm taking it to the other side. So it will be V2 into 1 by R2 plus 1 by R3 minus V1 by R2. I have the negative sign out of the bracket. So both the equations, now I and I naught, let us assume that this is equation number 5. So now this 2 and 5 looks very much identical except for this negative sign. This has a negative sign and this doesn't have a negative sign. See, V1 into this term, V2 into this term, minus V2 by R2 minus V1 by R2. Both are looking identical. So how you can express it? This is I naught is nothing but the negative value of this term. This is nothing but what is V2? V2 is nothing but the voltage that has been developed at node 2 into, that is the product of the voltage that has been developed in node 2 and the sum of the resistance, sum of the reciprocal of the resistance. Okay, sum of the reciprocal of these resistances, that is R2 and R3. What is R2 and R3 are the resistances that has been connected to the node 2 which is under observation, minus the ratio between V1. V1 is nothing but the adjoining potential. When you are looking at this V2 with respect to V2, this V1 is considered to be an adjoining potential. The ratio between the adjoining potential and the interconnecting resistance is this R2 because it is connecting node 1 and node 2. So this is one. So you find that I has a positive value here, I naught has a negative value here. Okay, so it shows that since if you look into the circuit diagram, I is a current which is entering into this node 1. Okay, I is a current entering into this node 1. So current which is entering into this node 1 will be considered to be positive. So I enters into this node 1. So I has a positive value. I doesn't have a negative value over here in front of V1. But if you consider this current I naught is a current which is moving out from this node. See, the direction of the current I naught is away from this node too. It is away, it is moving out, it is an outgoing current. So outgoing currents are considered to be negative. Okay, so since this is an outgoing current I naught, you have a negative sign that is attached to it. Okay, so this negative sign indicates that I naught is a outgoing current and this positive sign indicates that I is an incoming current. Okay, this is the basic expression for nodal analysis with current sources. Okay, so we have derived this derivation. Okay, thank you all for watching this video. I hope this video will be interesting and very much helpful to you. Please do subscribe. Thank you.